Hey guys, so in this video I'm going to talk about how you can actually find lift coefficient from Joukowski airfoils. Again, the reason why we need to do this is because for your research project you can design your own airfoil using Joukowski transformation, take that airfoil and run some inviscid simulation or simulations with some viscous subroutines using XFLR5 or Xfoil and actually get the lift coefficient and drag coefficient as a function of angle of attack. The reason why we need to do this is because, again, remember, for our research project, we are, replacing the airfoil of an ECA, replacing the airfoil of a Cessna 172. The Cessna 172 has an airfoil NECA 2412, but in here, you're going to replace it with the airfoil that you create using Joukowski transformation and compare how the airfoil that you created compares with the airfoil of Cessna 172, which is NECA 2412. Okay, here's a question which you're required to answer. So here you have the x and I will just read the questions to set some context. So get x and y coordinates of the cambered airfoil you generate from the last homework using Joukowski transformation, and use the MATLAB code I uploaded in Isidore under assignment tab to convert the x and y coordinates of the airfoil to a format which XFLR5 likes. So it's very important that you actually use the code that I upload, because without that, the airfoil that you created in MATLAB cannot be interfaced with the XFLR5 or Xfoil, because Xfoil likes its data in a certain format. So it's very important that you actually stick to the code that I uploaded in Isidore. Okay, here are the deliverables. You should determine the coefficient of lift as a function of drag, and also the lift curve slope, which means how the slope or the lift changes as a function of angle. And you'll be comparing the result of lift curve slope with 2 pi alpha. Again, we'll talk about the reason why 2 pi alpha and what's so special about that. And what we're going to do is you're going to also plot the variation of center of pressure. Center of pressure is a topic that we will cover in class, and in this, I will tell you how to actually plot the center of pressure using Xfoil or XFLR5. And in the end, the last one is you're going to compare the data that you get from this exercise with NECA 2412. Okay, just so that you understand what are the variants or differences between 2412 and Joukowski airfoil. Okay, now let me actually go to the MATLAB code. Let me open my MATLAB right there. So, all right. So, sorry. All right. Here's my Joukowski transformation code, which you already have, right? So I'm gonna run this code, and as you can see, I've created my Joukowski airfoil, right? So what I see here is what I recommend you guys doing here is that just for sake of for Xfoil and XFLR5, please keep these x0 and y0 values as small as possible. Okay, don't exceed them. Don't go like 0.4, 0.5, because the solution to the simulation will blow up in XFLR5. Okay, so keep it as in these order of magnitude as possible. One thing that I recommend doing is that after you transform your matrix, transform your airfoil, save the airfoil coordinates in 2 columns, like I can put here A and B, airfoil 1, 2, and save the airfoil as a .mat format. Okay, so when you do that, you can call the this airfoil mat using another file which I upload. Okay, so make sure you run this. Make sure that your folder has this airfoil mat saved. Okay, all right. Now once you do this, go to the code that I actually that I actually uploaded in Isidore. Okay, this code will help you convert the airfoil mat data set that you created into a format which XFLR5 likes. Okay, so all you have to do is make sure everything is in the same folder, and all you got to do is click run. Okay, now what you see here is a comparison of the refined airfoil coordinates for XFLR5, which is the actual data set you'll be uploading, and the airfoil coordinates that you get from the previous code. Okay. One thing to note is that around the leading edge, you will see some differences between the two curves, but this can be addressed later in the XFLR5 software. Okay. So that's all you have to do. One thing that you can name in this line, you can name your airfoil anything that you want, but I recommend saving as .dat file, which is the data file. Okay. Joukowski 33, just include your name, your friend's name, or whatever you like. Okay. Okay. And just double check that in that folder, you will the data of the airfoil will be stored as a .dat file. Okay. Now, minimize that. Let's open XFLR5. Okay. So this is my XFLR5 window, right? Now I'm going to open. I'm going to go to File and click Xfoil Direct Analysis. What that will allow me to do is to simulate airfoil shapes and determine CL and CD. Okay. Now I'm going to input the airfoil that I just created using Joukowski transformation. I'm going to go to File, click Open. I'm going to search the folder, and this is Joukowski 33. It's the airfoil that I created. So I'm going to double click it. Okay. Now you can see that the airfoil is actually in the XFLR5, right? And you see that towards the leading edge, it's sort of sharp. So do not run the simulation with this because your solution won't converge. Okay. Before you run the simulation, go to Design and then click Refine Globally. Okay. And in the number of panels, just put 200, or if you want, you can just even put 250. Okay. Click Apply and then click OK. And then it'll ask it to override. Right. So what we did here, we increased the number of panels that if you look at the leading edge, it automatically smoothed it for you. Okay. Now here is actually our airfoil, which is pretty cool, right? Now all you have to do is run the analysis. So go to Analysis, click Define an Analysis. I recommend you doing this at a different loss number. Just for demo purposes, I'm going to put it as 200,000 and click OK. Now you have this Analysis tab. Make sure that all the sequence is checked, because what this is that you're looking at how the simulation range of angle of attack. So it goes from -4 to +10, an increment of 1 degree. Make sure to check all these boxes, and all you gotta do is click Analyze. Right? As you can see, the solution is analyzing. Now look at that. You can actually see the CP graph, right? Which is pretty cool, right? So let me put it in a color that you can actually see. There you go. So you can see that the CP plot, and you can see how that changes for different angles of attack. Okay, and what's really cool is that you can actually look at the pressure variation or pressure difference or the pressure distribution across your airfoil, right? And you can see, and better yet, you can even animate it. So you can watch what the pressure difference is looking like on top and bottom of the airfoil as a function of angle of attack. Okay. Now remember that the CP that we talked about. So in class we will look at this pretty soon, but the CP in this graph is coefficient of pressure. Okay. There is another CP which is also called center of pressure. In the assignment, what I ask you to do is to plot the variation of center of pressure. Okay. Now that center of pressure is nothing but, you see this arrow right here? So let me animate. Right. You see what's happening to the center of pressure? This arrow as you change the angle of attack. Right. This is what you will be plotting. Okay, as a function of angle of attack. So this arrow represents the center of pressure. Is a pressure, it's sort of like center of mass, where you represent the entire mass distribution in one point in the object. In the same way, center of pressure is basically, it's a point where all the pressures can be thought you can consider all the pressures that are acting at that point. Okay, and that actually moves as a function of angle of attack. Okay, which is pretty cool. Now, if you actually click this tab right here, you can see the variation of CL as a function of angle of attack. Once again, let me increase the color so that you can see it right there, right? So here you can see the CL versus function of alpha, right? Now, all you have to do is, you extract this. Again, don't screenshot the XFLR file or Xfoil and place it directly in your portfolio. Go to current graph, and then you can actually export the graph. Okay, so that means you can export CL and alpha. Similarly, if you go here and if you want the CP distribution, go to current polar, and then you can export. Okay, and here you have CP graph, and you can also export. You can export any data that you want. Okay, so just make sure that you export the data and plot it in Excel or MATLAB so that it's easier to see, because the dark background and not so bright colors may not look well in a Word document. Okay, so this is pretty much what you're supposed to do for this question. Okay, if you want to do a great way to actually simulate NACA foils is that there is a NACA foil already inbuilt into XFLR5. So if you want to do 2412, just go like foil, click NACA foils, or to design good NACA foils, and just do 2412. Okay, and then click OK. Click OK. Now here you have the 2412 airfoil, right? So I'm going to do the same analysis. I think I'm going to do 200,000. Click OK, and I'm going to analyze. Right. So here is a variation of CP as a function of angle of attack. Right. Look at that. Now what I can do is I can go here and look at that. I compared the green line is NACA 2412 and the white line is my Joukowski airfoil. Look at what happened, right? These Joukowski airfoils shows somewhat of a little bit of higher lift coefficient, right? Which is great. But remember that XFLR5 is an implicit software. Even though it accounts for there are some viscous subroutines in here, but it's all mathematical or numerical estimation. It's not solving actual Navier-Stokes equation. Okay, so hopefully you'll get you got an idea of what you're supposed to do for this problem. Okay, let me know if you have any questions.